So last time we talked about this Ginzburg criterion, which allows us to check whether the Landau's theory works okay or the Landau theory breaks. And let me summarize this Ginzburg criterion one more time. This little t, which is the dimensionless quantity measuring how far or how close the system is close to transition temperature, Tc. And when the little t is larger than this Ginzburg-Landau distance, PLG, Landau theory works okay. In other words, this arrow bar we defined to check whether the fluctuations effects are important. If this ER is small, then the fluctuations are not important. So Landau's mean field theory works fine. However, on the other hand, when this little t is less than TLG, then this arrow bar is big. It's order of 1 or even larger than 1, then the Landau theory breaks down. And the most important quantity is this TLG here, which is defined by those prefactors, but most important quantity is C1, which is the correlation length when temperature reaches 2 times Tc. And this quantity depends on the range of interactions, which we already demonstrated. So using a figure is easier to actually understand this Ginzburg criterion, in the sense that if we're talking about the finite temperature phase transition along the vertical line, where this low temperature region is a ordered phase and high temperature region is a disordered phase, and the transition line is indicated here in this curve, Tc curve, and within the range of order of this size, which is defined precisely by the Ginzburg criterion, where this little t is the same as this TLG, and we define this critical region above and below this Tc line. So within that critical range, the Ginzburg criterion is violated or the Landau theory breaks down. So we need to take special care when we calculate the observables inside this critical region. Okay, but out of the critical region, we are fine. So we could actually give some estimations of how large or how small the size of the critical region is in the more realistic systems or regarding to this well-known examples in solid-state systems. So, for example, in the magnetic materials, where we show some kind of a magnetic ordered and disordered phase below and above transition temperature. So in such a case, this C1 is the order of angstrom, 1 angstrom. So it's really small in size, and translating into this TLG is about order 1, but which is really, really large. So which means that this critical region is really, really large, and it is easy to actually make this Landau theory breaking down. So which means that its fluctuations factor very, very easily to be seen. So another case or example is the superfluid helium-4, where this C1 is order of 1 angstrom and TLG is the same order of magnitude as the magnetic system. So in these two systems, the mean field theory or Landau theory breaks down very easily. So we need to pay attention to that when we very close to Tc. So on the other hand, for superconductors, this TLG can be very, very small. For example, in the BCS superconductors, where ordinary metals, when the temperature is low enough, they become superconductors, and they are mediated by these electron-phonon couplings. So in those weak coupling BCS superconductors, C1 is about 1,000 angstrom, which is the size of the Cooper pair. And in particular, for three-dimensional metals or the BCS superconductors, this TLG goes that small value, 10 to the minus 16, which is really, really tiny, which means that this critical region is really, really small. And we don't even see that tiny little bit critical region, which means that the mean field theory works extremely well, exceptionally well, and unexpected well. So we don't expect that this mean field theory can work that well. But now we know the reason. The reason is that this critical region is really, really tiny. If we plug in all the numbers into the Ginzburg criterion, and so that's we should say the coincidence, but it's not a coincidence. So, but it is a very rare case in physics that the mean field theory works that well. So the next example is the high Tc superconductors in cuprate, where the Cooper pairs are made of spin-on pairs rather than this electron phonon mediated Cooper pairs. And in that case, this C1 is about 10 angstrom, which leads to the TLG is about 10 to the minus 5. And another interesting system is the thin film superconductors, which also show the same order of magnitude in TLG. And it looks quite small, but it is large enough to see this fluctuations effect as we go closer and closer to the critical temperature. So that's the realistic estimation of how large the critical region becomes at the finite temperature transition. So a special remark here, we want to emphasize that as dimension is less than 4, the upper critical dimension, this quartic term proportional to phi to the order of 4 is going to be increasingly important as you approach this critical temperature. And in that limit, this perturbation theory actually breaks down. So we mentioned last time that the upper critical dimension is 4. So for D is less than 4, then we have a problem, because then this ER is going to be very, very large as this little t goes to 0. But for D is larger than 4, the mean field theory works well. So as you approach this critical temperature, then this error bar is still very, very small, or even vanishes. So that mean field theory can be very, very good. Okay, so let's take a short break. When we come back, we will try to compute this two-point correlation function, or the Green's functions, by directly evaluating this partition function from this functional integral approach. Let's take a short break. So now we will introduce a different approach which will be very useful when we study field theory regarding the phase transitions. So we try to repeat the calculation that we did earlier for the Green's function, g, as functions of the distance between these two spatial vectors r and r prime. But this time, we try to directly compute this functional integral. Remember, in this coarse-grained formalism of the Landau theory, we try to form clusters of those spins, and we could separate these partition functions in terms of partial trace over this coarse-grained microscopic degree of freedom inside this single clusters, and also you sum over all the clusters. So in the continuous limit, this is equivalent to this functional integral over these mean field variables, eta or phi, and inside this integral is the exponential minus beta, this Landau's free energy functional. And so we could directly compute this thing within so-called Gaussian approximation, where in this Landau functional, in general, we have this constant term and the even power of this mean field order parameter, phi squared, and a quartic term, phi to the power 4, and also the gradient square term, which take care of the difference between the maximization order parameters among all these different clusters, and also external field. But out of this critical region, so as little t is not so close to this TLG, then we could forget about this quartic term, get this phi to the power 4. And if we neglect this term, we call this Gaussian approximation. And under such a Gaussian approximation, we are able to obtain all these nice properties of this two-point correlation functions that we already derived some time ago. Under such a functional formalism or functional integral method, we are able to construct more generally the correlation functions and more systematic calculation by using this functional integral method. And it will be useful when we really introduce the field theory of phase transition. So this functional integral method becomes very, very useful and convenient and important. So let's just do this integral. Remember, this integral is a bunch of the product bunch of this different mean fields over different clusters, right? So d phi 1, d phi 2, and so on and so forth. So in the continuous limit, where this lattice constant becomes almost 0, then those variables become continuous variables. So we could simply consider this as a continuous integration over all different, say, mean field variables. And remember, this Ginzburg-Landau free energy takes this form in the absence of the external field and also no quadratic term. So this Gaussian form of the Landau's free energy takes that simple form. We have only this quadratic term phi square and also the gradient phi square, so which can be diagonalized easily. So to diagonalize this, we could Fourier transform this order parameter phi of r in K space. Okay, so this is kind of a discretized version of the Fourier transform, but we can make it a continuous limit where this integration, this summation over there becomes the integration over dk. And if we do so, we could rewrite this Landau free energy in terms of this momentum sum. Okay, so you simply just plug in this Fourier transform of this phi of r, and also you take this gradient and you square it. You get this k dot k prime. And then, but you need to conserve the momentum, and otherwise you get 0 because of delta function. So there's a delta function here. So this delta function tells us that if k is not equal to k prime, this is 0, and if k is not equal to minus k prime, but if k is the same as minus k prime, then you get 1. So you could convince yourself that the reason why you get this condition that k has to be equal to minus k prime, or you could simply just plug in this Fourier transform. You get this same type of this Fourier series, e to the I k dot r and e to the I k prime dot r. So you need to add these two exponents together, so you get k plus k prime, but when you integrate over this dr, you get a delta function. So that's precisely what this delta function comes about. Okay, so you plug in this delta function, you get this, you flip the sign here because k prime equals to minus k, then this becomes k squared. The double negative is actually plus here. So this is a very simple form of Landau's free energy in K space. And so we need to take advantage of such a Fourier transformed Landau's free energy under Gaussian approximation. So remember last time when we defined this Fourier transform of the order parameter, so we argued that there's a symmetry between this order parameter in K space between the positive K and negative K values. So there are only half of the degrees of freedom in K space are really independent, okay? Because the other half of the K points are related to the plus or minus the other side by this relation. The complex conjugate of the phi is actually phi minus k. And so you could decompose this K space order parameter into the real part and the imaginary part, which I call this x and y respectively. And then this integral over d phi, okay, now becomes the integration over separately the real part and the imaginary part of the order parameter. Remember, we limit ourselves to the K space of just the positive side of this momentum variables, so that there is a prime here in the product of those little d phi k. So now we want to evaluate this integral, but this integral can be done very straightforwardly from this so-called Gaussian integral. So this is nothing but the Gaussian integral. So we will continue calculating this Gaussian integral in just a moment. So let's continue evaluating this Gaussian integral. So if I plug in this real and imaginary part of this order parameter field in the K space, then I get this kind of the product of all this double integral, okay, over the entire momentum space. And I can take advantage of such a Gaussian integral, where if you integrate over this dx from negative to plus infinity of this e to the minus a times x squared, you get square root of pi over a. And if you evaluate this double integral by multiplying these two single integral together, you get the square of the square root of pi over a, which is pi over a. And a is the constant independent of this x and y. So now this a of k, as I already showed, is given by this kind of Fourier transform of this Landau free energy functional, which takes this form, k-dependent form, but not this a of k is independent of the x and y, so you can consider this a of k is just a constant. So if I use this Gaussian integral result, I get this final result. Not final yet, but almost there. It's the product of this momentum k in half of the k-space values and the product of this pi over ak. And then this free energy, Landau's free energy e to the minus beta f in the partition function now take this form. And so you take the logarithm of this equation on both sides, you get Landau's free energy in terms of this sum over k of a log of this stuff, and of course it can be shifted by a constant a0 times the volume. So from this Landau's free energy, we are able to get all these correlation functions by taking this functional derivative of free energy with respect to this phi. We are able to get all this correlation function. But there's a trick or a shortcut to actually evaluate this phi-phi correlator in this momentum space, which is a Fourier transform of this phi-phi correlator in the real space x and y, and which we define this as a volume times the Green's function g in k space. So there's a shortcut to get this g of k is by the equipartition theorem in statistical mechanics, where the kinetic energy, if you sum over all this direction in ks, ky, and kz, you get 1/2 of the kbt. But now you get twice as many as this degrees of freedom, because phi k runs from this plus to minus k. So there's a factor of 2 here. So once you know this trick from this equipartition theorem of statistical mechanics, then you immediately get this k-space representation of this Green's function, g of k, which is nothing but this. And from this, we easily obtain all sort of exponents, beta, gamma, nu, and so on and so forth, that we already obtained. But this is just a shortcut, and next time we will formally just try to evaluate things based on this Landau's free energy in Fourier space. So that's about it for today, and we will continue next time.